We are talking about UMVUs, and I think, if I recall correctly, we did several examples of UMVUs. So I think we did maybe the Bernoulli and the normal with 2 unknown parameters and the uniform 0 theta. So I'm going with that unless you tell me otherwise. And while you're thinking about that, I'm going to share my screen. I don't know if I already shared this with you. I impulsively bought another tortoise last week who's arriving next week. And I'm going to have to move. I'm going to have to move out of my house of 20 years because he's going to get to 600 pounds. Nice impulse buy. Yeah, he's an Aldabra tortoise, which is second in size only to the Galapagos tortoises, but they're pretty close. Let's do one more UMVU, and then let's get into minimal sufficiency. So the final UMVU I wanted to do is to start with x1 through xn, IID uniform 0 theta. Now we already found the UMVU for theta, and it was based on the maximum because we have 2 steps to the Lehmann-Scheffé theorem. Step 1 is to find a complete and sufficient statistic, and step 2 is to find a function of that statistic that is unbiased for what you want. So let's find an UMVU for tau of theta equals theta squared. So because I meant to recap this, but I didn't, so I'll just sort of put that into my problem. By the Lehmann-Scheffé theorem, we have to do 2 steps. Step 1 is to find a complete and sufficient statistic S. Now, this is almost always done by exponential family, but for the uniform 0 theta distribution, that's not going to work. So usually exponential family factorization, but that doesn't work when the parameter's in the indicator. It also doesn't work in some other cases. I'm not sure if I talked about this last time, but it doesn't work, for example, for the Cauchy distribution. And if you look at the Cauchy distribution, it doesn't have any indicator because it lives on minus infinity to infinity. And it's hard to show that something is not exponential family, but the general approach is to assume it is and assume that the joint PDF for the Cauchy distribution can be written as some A of, I think in my case on the table, there's a beta, A of beta, B of X, E of etc., and try to establish a contradiction. You don't have to worry about it for this class. But yeah, so this is usually exponential family, but it's not for the uniform. But we already established this a few times now. The maximum is complete and sufficient. And we did that by using the factorization criterion to show that it was sufficient, and then showed completeness the long way by the definition with the expectation equals 0 definition of completeness. So this we've already determined, and this could take a lot of work to show if you don't have an exponential family factorization. So already known. Okay, so step 2 is to find a function of the maximum that is unbiased for the target theta squared. I'm going to go ahead and call, well, I already called it tau of theta. So if I had done this example directly after the last example in the last class, we would already know the expected value of the maximum. I'm just going to recap that super fast. I know the maximum lives on 0 to theta, and I'm going to take x times the PDF for the maximum. You may not know the PDF, and that's fine, but it looks like this. And so I end up getting n over n plus 1 theta. and I purposely didn't show any detail there, but I just wanted to say that it's not theta squared. So we're going to try the expected value of the maximum squared, and hopefully we'll see a theta squared. This is going to be the integral 0 to theta of x squared n over theta to the n x to the n minus 1 dx. And so when you combine these, you get an x to the n plus 1. And when you integrate that, you get x to the n plus 2 over n plus 2. And when you plug in theta, you get theta to the n plus 2, but you also have a theta to the n, you get some cancellation, and you end up with n over n plus 2 theta squared. So the estimator that is n plus 1 over n times the maximum squared is the umvu for theta squared by the Lehmann-Scheffé theorem, because there's two steps. One, find a complete and sufficient statistic. Two, find a function of that that is unbiased for the thing you want. And clearly, note, oh, that's not my theta. That's the estimator for tau of theta. So I actually want a tau of theta hat here. So the tau of theta hat umvu is not tau of theta with the umvu plugged in. The umvu, because I know the expected value of the maximum is this, if I wanted to find the umvu for theta, I would, yes. Wow, I thought I didn't flip it, but yeah, this should be a 2. I was just trying to move this to the other side and failed miserably. But the umvu for theta is n plus 1 over n times the maximum. And if you square that, you do not get n plus 2 over n maximum squared. So not invariant. And that's totally expected because expectations don't work like that. Like if you want to estimate mu squared for a distribution and you try x bar squared, it's not going to be quite right. So umvu's definitely not invariant in general. Great. So your homework that's coming out is going to be mostly umvu's. This is your last homework, and it's due the Wednesday after Thanksgiving. It's going to be mostly umvu's and one half of a proof that I want to do today involving minimal sufficiency, the easier half. So what is minimal sufficiency? A statistic being minimal sufficient. I think we have a sense of what that is. And some people, some textbooks, you define minimal sufficiency to be what I think is our sense, but that's actually wrong. So let's talk about minimal sufficient statistics. The informal and actually wrong definition, but it will probably work for you most of the time, but I'll give you an example as to why it's wrong, is that you have a model, you have an x1 through xn, and they have a joint PDF. And a statistic S is minimal sufficient if it is a sufficient statistic of lowest dimension. And this is not right, and I'll tell you why. But it's kind of the idea. So again, this is wrong, but again, the idea, we saw for the uniform 0 theta that the entire n-dimensional vector of data is sufficient, and we saw that the min and max together is a 2-dimensional sufficient statistic. why not throw in the sum of the x's? That won't hurt. The min, the max, and the sum of the x's is a three-dimensional sufficient statistic, but we eventually got down to the maximum. And that has to be the lowest dimension because we're down to dimension 1. But this definition could steer you wrong. So it kind of works practically speaking, but it's not the literal definition of minimal sufficiency. So I want to give that to you now. The definition that is formal, have the same setup, and x1 through xn with some joint PDF. So a statistic S, this is some S of the vector X, is minimal sufficient if it is two things. If number one, S is sufficient, and number two, S is minimal. No, just kidding. That would not be a definition. So it's got to be a sufficient statistic, and it is a function of any other chosen, any and all other sufficient statistics. So any other sufficient statistic, I guess. So as an example, in the uniform 0, 0 theta case, yeah, that is what I want to do. So we had 3 sufficient statistics, and there are more. We tried the factorization criterion, and we didn't simplify the indicator, so we got that the full data set is sufficient, and we got that just having the min and max is sufficient, and we got that the max is sufficient. And there are more things, but like this S3 is a function of S2, and that function is to like some g of xy defined to be y. And it's certainly a function of S1 because you can get the max from having those n values. And so this doesn't prove that this is minimal sufficient because I haven't looked at every possible sufficient statistic. And in general, it is hard to prove minimal sufficiency, but I have a very weird theorem for you that is going to help. So before I state and prove that theorem, I want to talk about the idea of dimension. As I was saying, a lot of textbooks will say that if you have something sufficient of the lowest possible dimension, then you're good. The lowest possible dimension is not always clear. It is possible to have a model with 2 parameters and to have everything sort of cancel, and you can actually describe it with a 1-dimensional sufficient statistic, but that doesn't always happen. So if you have 2 parameters and you get down to a 2-dimensional sufficient statistic, you're not sure if you have the lowest dimension, but for any 1-dimensional sufficient statistic, you are down to the lowest dimension. And my claim is that's not enough to say it's minimal sufficient by the formal definition. That was way too many words. So this is an example of lowest dimension sufficient is not necessarily minimal sufficient. So if you take just a sample of size 1 from the normal distribution with mean 0 and variance sigma squared, x1 is sufficient. All right, it's the entire vector of data. You can certainly factor the joint or the PDF for that one into some x only and x mixed with parameters, and you could get it by the factorization criterion. But so is, for this particular problem, if you looked at this PDF, you can write it as a function of x1 in absolute value. So this x1 an absolute value is a function of x1, but not the other way around. Because if you have the absolute value, you can't recover the thing inside. You need to know the sign. So I want to finish this line up here, but it is not minimal sufficient because this is also sufficient and x1 is not a function of it. Just a minor technicality that I'm not even sharing with baby math stats. And it's more for your information than something you need to worry about for this class. And I would suspect also the prelim, but I can't guarantee when different people write the prelim, but this sort of thing has never made it on there. So it's really hard to find, oh, is that an old message? No. It's really hard to find minimal sufficient statistics, and I have a bizarre theorem for showing something is minimal sufficient. I would write bizarre, but then I would have to spell live again. 2 Z's or 2 R's? Bizarre. I don't know. I'll call this the ratio theorem. Doesn't really have a name for minimal sufficiency. Why do we care? Why do we care about this at all? Because I have some things coming up that will allow you to use minimal sufficiency to establish independence of some random variables. So you might find yourself in a situation where you need to show one variable is independent of another, and you can't write the joint PDF or do anything else, but you can use a minimal sufficiency argument. Okay, so here it is. I'm going to take x1 through xn with joint PDF f of the vector x and theta could be a vector valued. And I'm going to let S be some statistic. I'm going to take a vector x and y, so just any vectors in the support of the joint PDF, and define the ratio R of x comma y semicolon theta to be the joint PDF evaluated at x over the joint PDF evaluated at y. It's still only one PDF for the x1 through xn. I'm just using y as a different argument to plug in. Okay, and this is still part of the setup. So suppose this weird thing holds. Suppose that R of x and y and theta is theta free if and only if the s of little x is equal to the s of little y. So that's not something to show. It almost looks like something to prove, right? Starting with one, you get the other and back. But this is actually an assumption of the theorem. And here is the punchline. Then S is minimal sufficient. I think that's a strange looking thing. I don't know what you think, but I want to prove half of this today. I want to prove what I think is the harder part, and that is to show that S is sufficient. And then on your homework, you're going to get to show that it's minimal sufficient, which is not as bad. Before proving it, I want to try an example to how we would use this theorem. So as an example, suppose I have x1 through xn IID Poisson with parameter lambda, and I want to find a minimal sufficient statistic for this model. So I'm going to look at the joint PDF. I'm going to form the ratio. I'm going to make sure that this weird condition holds. Sorry, not that, the next one. I'm going to make sure that this weird condition holds for some statistic S, and then I'll be able to say it's minimal sufficient. The joint PDF here as a function of X and lambda is E to the minus N lambda, lambda to the sum of the X's over the product as I goes from 1 to N of the Xi factorial. And an indicator, I guess it's important. The product as I goes from 1 to N of the indicator, saying that each Xi has to be in the set 0, 1, 2 on up. Oops. Yeah, the X and Y are just vectors from the support of the PDF. So just given fixed vectors. Okay, I'm going to form the ratio. So that's when I just take this thing above and I write it down, and I also write it with Y's and cancel stuff. So I won't bother to write that huge numerator and denominator. Let me just write this part and then what it's equal to. If you form this ratio, so take the thing I circled and put it over the thing I circled with Y's plugged in, this E to the N lambda is going to cancel. And not much else is going to cancel. Nothing else is going to cancel. So I'm going to be left with lambda, the sum of the X's minus the sum of the Y's. And I'm going to have a product of the Y's over a product of the X's and products of indicators. So a product of the indicators for the X's over a product of the indicators for the Y's. And so this involves lambda over here, but we can see, oh yeah, both are vectors of length n. I need to look up at the chat more. Yeah, I just took any x1, I just took any vector x and y in the support of the distribution and of the joint, sorry, of the joint PDF. And yes, I forgot the factorial. So x and y are any vectors in the support of the joint PDF. And yes, I forgot my factorials on these products. But you can see that this thing is going to be theta free if and only if this is equal to this. So this R, this ratio is theta free, I mean lambda free, if and only if the sum of the X's is equal to the sum of the Y's. So the statistic S, defined to be an S of X, I guess I want this capital now, defined to be the sum of the X's. So back here, I've got S of the little x's equals S of the little y's, is minimal sufficient. I don't know what people call this. I've never really heard a name for it. So I'm just going to call it that ratio theorem for minimal sufficiency. There are distributions that have no minimal sufficient statistics. That is a great question. I know of one only, and it was shown by a statistician named Bahadur. And it is a really weird pathological example. I believe that all discrete distributions have minimal sufficient statistics, and all continuous ones have minimal sufficient statistics. But he made up a very strange example that is sort of continuous, but it has a point mass in certain places. I never remember the example. I'm going to try to find you a reference. So this guy has, I'm just going to write this for now, an example of a distribution where no minimal sufficient statistic exists. But you're not going to come across that. It was one of these strange pathological examples designed just to do that. Okay, I want to prove this theorem. Before proving it, I want to talk about something that it really will make up the bulk of the proof, but I don't want to do this part in the proof because it's kind of a big aside. And that is to attach sufficient statistics to partitions of the support of the joint PDF. So there's lots of words going on in here. So some subset of Rn where the PDF is non-zero. Okay, so suppose I have, let me just, got that. I just want to go to a full slide. Suppose I have this box representing Rn, and then this set representing the support of the joint PDF. So the joint PDF is 0 outside of this set and non-zero in the set. And I want to consider, I know I can fit this above, consider a sufficient statistic S, which is going to be some little s of the vector x. So if I take the support of f and I put it through that function, little s of x, then I will get the image of that function. So this is going to be in some space. It's going to be maybe R or RK. So it's going to be R if the sufficient statistic is one-dimensional, but if it's two-dimensional, like this is the min and the max, then this set on the right would be R2. So we get some kind of like the range of the S of X function. So I just started with a sufficient statistic and just sort of drew a picture. It's taking the support to some set. And so now consider any, I'm going to take any S in the range or image of the statistic S. And I'm going to define some sets. I'm going to define A sub S to be all of the X's in the support of the joint PDF. So I'm just going to write support of F such that S of X maps to that fixed little s. So the pre-image of that point little s, that is, I want to make this bigger so I can draw some things. So the pre-image of a point little s, everything that maps to it, you know, it might be some set over here that maps to that point. So note that the collection of these sets, they partition the support of F because every point in this blob goes into this blob. And so because it's a function, then the pre-image of two separate points are going to be disjoint sets. So if you go back and you look at all of the A's, they're going to make a partition here. So then the set of AS's for S in the range of S is a partition of the support of F, meaning the joint PDF. I think this might make more sense with an example that goes to a discrete space. So if this is Rn, and then I have the support of the joint PDF, and maybe a statistic. So this is really a specific example trying to help me illuminate what I'm writing here. I went back to that S again, S of X. So say it could only map to 1, 2, or 3. Then I can break up the support into 3 sets. They won't necessarily be like contiguous, but I would call it A1, A2, and A3, A1 being everything that maps to 1, A2 being everything that maps to 2, etc. Okay, so suppose that S is minimal sufficient. And let T be any other sufficient statistic. So the statistic S induces a partition. It's the one we just saw. A partition of sets AS for all S in the range of S. It induces a partition of the support of F of, I'm going to write the vector to be more clear because F is sometimes the single PDF. And T will induce its own partition. I guess I haven't used sufficiency at all yet. So its own partition. I'm going to call this B of T. So a bunch of sets B. The T could be continuous, but in my simple example, like a B1, B2, B3, maybe B4 and B5. It doesn't have to be the same number of sets because I'm using a totally different statistic. So this is going to be indexed over the range of T where that statistic function takes you. And this is not going to be another partition of the support. So I claim that the minimal sufficient statistic has the coarsest partition. So I claim that each and every BT is a subset of an AS for some S. Let me just try to convince you by example. Maybe you're convinced already, but in the uniform 0 theta case, we talked about S being the maximum is minimal sufficient, although I haven't proved that. We only proved so far a minimal sufficient statistic for the Poisson. So that's still just a claim. And T being the minimum and the maximum is sufficient. Okay, so if I take a BT and write that out, this is really, because of the space, a T1 and T2, because my T statistic is 2-dimensional. And this consists of all of the X in the support of the joint PDF such that the minimum and the maximum of that vector, so these are lowercase and not random variables, is equal to T1, T2. And this is kind of more restrictive than I can say that, what am I trying to say? Oh, yeah, I'm trying to say this is a subset of the x's in the support of F, for which the maximums of those vectors map to T2, which is the definition of a T2. So starting with any BT, we're able to find an A that contains BT. Okay, so this is telling us that, and by the way, the A partition came from the minimal sufficient statistic. And this is also not a proof, but you can see that because the AT is defined by a function of what the BT is defined by, that when you take other sufficient statistics that are not minimal sufficient, you are making a finer partition of the space, because you want not just the maximum to be T2, but the min and the max to be T1 and T2, which is going to be some subset of the support where the max is T2. Does that make sense? Again, the whole point of this is to say that a minimal sufficient statistic makes a partition, they all make partitions, and corresponds to a coarsest partition of the support of the joint PDF. Some people, in fact, define sufficient statistics and minimal sufficient statistics through subsets in RN, so subsets of the support of the joint PDF. They approach it from the beginning in terms of these partitions. And the reason I bring this up right now, I don't usually talk about this because I don't know, we got other things we can do, but that I think would be more fun. But the easiest way I know to prove that weird ratio theorem uses this support structure, this support characterization of a minimal sufficient statistic. So I was excited to see proof of sufficiency for that theorem, not that theorem, the ratio theorem. I have two things to show. Well, I have to show that the statistic is minimal sufficient. So I have to show it's sufficient and then it's minimal. And so I want to show the sufficient part and leave the easier minimal part to you. Okay, so I can go back to the proof of that theorem. This is a very long theorem, but I really think we need to see it again. So I'm going to copy and paste it rather than spend the time writing this out. Oh, I didn't mean for that to happen, but okay. So there is the theorem again. Oh yeah, is the minimal sufficient statistic unique up to anything? It is unique up to one-to-one transformations. You can imagine in this ratio characterization in the Poisson case, I could have said 2 times the sum of the x's is sufficient, and even more interesting one-to-one transformations. So not unique, but unique up to one-to-one transformations. Should I bother to do this? I think I can do this quick enough. So, and I didn't copy and paste the whole thing. Then S is minimal sufficient. Okay, so the proof of sufficiency, and then you get to prove minimality, which I think is easier. So I'm gonna look at a partition of this just isn't going to work in the time we have. It's actually short, but I think each step requires a lot of thought. So let me just do a couple of steps. I'm going to let S tilde. So this is a set, and it is connected to the statistic S, which is up here. But it's a set, not a statistic. So I called it S and put a tilde on it. I'm going to let this be all of the S's for which S is some S of X for some X in the support of F. So this is the image of the function S of X. And I'm going to let A sub S for S in this S tilde be the induced partition. And now I'm going to say for each set AS, and this could be continuous, so this index does not have to be discrete. I'm going to choose a point, any point, and there is an axiom of choice thing happening here if you care. I don't want you to have to worry about that kind of pure math, but there is a point in each set, and so you need to choose one. So for each AS, choose and fix a representative point. And I'm going to call that X sub S star, like it's this great representative thing in each AS. And I think that is one more thing I can fit in here. If you imagine the support of the PDF broken up into a partition of 3 sets, going to 3 different points, which is a very simplified example, then right now I have fixed a single point in here called X1 star and a single point in here called X2 star and a single point in here called X3 star. And it doesn't matter which one, but I've gone into each set and grabbed a number and fixed it. So what's going to happen next? Who knows on mathematical statistics? Thank you.